In this video, we're going to be talking about set operations. In the previous videos, we saw how to use set notation to write down sets, for which it's very hard to just enumerate all of the elements of the set inside brackets. And the way we do it is using this other notation that also involves brackets, but involves this sort of different way of writing it. And the way we write it, and going back to this example, is open the left curly bracket. That means the set of all. And then whatever variable or object you're going to be working with, we're going to be calling them x. The colon means such that, and then after the colon, you write down whatever properties these objects have, right? So the defining properties of the set. For this particular case, we're looking to write down the set of all even integers, right? So what are the properties that x have to have? Well, it has to be an integer, so x is an element of the set of integers, and it has to be even. So, and x is even. Right? And those are the properties that define the elements of this set. So another example, we wrote down the set of rational numbers, and we did it the same way. Open the left curly brackets, that means the set of all. And then what are the symbols we're going to use now, or the objects? Well, objects that look like x over y. And such that, what are the properties that these objects have? So after the colon, well, it's the properties that x is an integer, y is an integer, and y is not equal to 0, because we don't want to divide by 0. And that is the set of rational numbers. Now, we can't write down the set of real numbers that easily. In order to do that, we need to use or introduce set operations. So the set operations are very easy. You'll see that they're very intuitive. So let's start with the first one. So definition 3. So given sets S and T, so it's any sets S and T, if every element of S is also an element of T, then we say that S is a subset of T. We denote this by, so denoted by S, and then this sort of symbol with a horizontal line, T. So let's see an example. This would be example 3. So I'm going to give you two sets. Or let's start with this. Let's just do a couple. So the set of natural numbers is a subset of the set of integers. Why? Because every natural number, if you look at the definitions here, commonly used sets, every natural number is also an element of the set of integers. Right? 0 is in there, 1 is in there, 2 is in there, etc. Right? So the set of natural numbers is a subset of the set of integers. And this you want to read as is a subset of. Okay, that's one example. So another example, the set of integers is a subset of the set of rational numbers. Why? Well, look at the definition of the set of rational numbers. It's a set of all x over y, such that x is an integer, y is an integer, and y is not equal to 0. If we set y equal to 1, right, then we're just looking at the set of all x over 1, such that x is an integer. Well, x over 1 is just itself. So really, that's just the same set as a set of integers. So let me make a note of that. Set y equal to 1 in the definition of the set of rational numbers. Okay, now let's do another example. Let's use finite sets here just to show you how it works. The set containing the elements 0, 1, and 2 is a subset of the set containing the elements 0, 1, 2, 3. Why? Look at any element in this first set. 0, okay, that's in the second set. Okay, 1 is in the second set as well. 2 is in the second set as well. So every element of this set is also an element of this set. Okay? But if we have the set 3, 4, this is not a subset, and you denote it by using the subset symbol and then doing a line through it, kind of like what we did with not an element. This is not a subset of the set 0, 1, 2, 3. Why? Well, 3 is in the first set and it's also in the second, but 4 is in the first set and it's not in the second. So there's an element of this set that is not in this set. And for this set to be a subset of the other, every element in the first set has to also be an element of the second set. And we see that it's not the case here because, again, 4 is in the first set, but 4 is not in the second set. Okay, so that's what it means for a set to be a subset of another set. Every element in the first set is also an element of the second set. Now let's introduce another operation. It's definition 4. So given sets, again, S and T, we're going to let the symbol S-U-T, this kind of looks like a U, and we read it as union. So let S union T be defined as, so what is this set? It is the set of all X such that X is in S or X is in T. And we denote this by using set notation. We'll just write this as the set of all X. Remember, the leftmost curly bracket means the set of all X. Colon means such that. What are the properties that we need? Well, this is the set with the properties that X is both an element of S or an element of T. So let me give you an example of what this looks like. So this would be example 4, I believe. Yep. So example 4. So if S is given to be the set containing the elements 1, 3, 5, 6, and T is the set containing the elements 1, 2, 3, 4, then what is their union? And this is very easy to check. Basically, any element that appears in at least one of the sets is included in this union. Okay? So 1 is in the first 2 sets, that's in there. 2 is in the second set. It's not in the first set, but it doesn't matter. As long as the element is included in at least one of them, you include it in the union. So we include 2. 3 is in both of them, so of course we include it. 4, again, is only in the second set, but that's enough. So we include it in the union. We include any element that is in at least one of the sets. Okay? 5 is only in the first set, we count it in, and then 6 is only in the first set. And that's how the union works. Basically, look at all of the elements that appear in at least one of them and write them or include them in the union. So that's the union operation. Now let's do the intersection operation. So again, definition 5. So given sets S and T, let S, and this symbol is called the cap, S cap T, and this symbol means intersection. So before the upward looking cap is a union symbol, the downward opening cap is an intersection. So let S intersection T denote the set of all X such that, what are the defining properties? Well, X has to be in S and X has to be in T. So notice the difference between intersection and union. In union, we use the word or. In intersection, we use the word and. That means that we only want to include elements in the intersection if that element is in both of the sets. So let me give you an example. Let me use the same sets as before. This would be example, let's see, example 5. So again, the same sets as before. So if S is equal to 1, 3, 5, 6, so the set containing this element, and T is equal to the set containing the elements 1, 2, 3, and 4, then what is our intersection? Well, we look at elements that lie on both sets. So one is in the set S, and one is in the set T. Okay, so one lies in both sets, so we include it in the intersection. Okay. 2 is in the set T, but 2 is not in the set S. Since 2 is not in both sets, we don't include it. 3 is in S, and it's also in T. It's in both sets, so we include it. 4, again, is in T, but it's not in S. It's not in both sets, just in one of them, so we don't include it. 5 is only in S. It's not in T, so we don't include it. And 6 is only in S, but it's not in T. It's not in both of them, so we don't include it. So the intersection is just the set containing the elements 1 and 3. And again, these are the elements that are in both sets. Okay. Now, one more set operation to introduce. This is going to be called the set minus operation. So definition 6. So again, given sets T and S and T, let T, and then you do this line like this, S, and so it's kind of like a, what's the word? Not a bracket, but a slash. Yeah, it's a slash, right? So T slash S, and you read this as, so this one's a little bit harder to read. We read it as T set minus S. So let T set minus S be defined as the set of all X with what properties? Such that X is in T, but, or, not but or, and X is not in S. So now we're looking for elements that are in T and not in S. So again, let's do one example. That should be enough for us to see how this works. So using the same set as before. If S is the set containing the elements 1, 3, 5, 6, and T is the set containing the elements 1, 2, 3, 4, then what is T set minus S? Well, look at all of the elements of T. Any element that is also in S, you remove. So let's see. 1 is in T, okay, good, but it's also in S, so we can't use that one. Okay. 2 is in T, and it's not in S, so we include 2. 3 is in T, but it is also in S, so we don't include 3. 4 is in T, and it's not in S, so we're good, we include 4. And that's T set minus S. Now notice that by definition, T set minus S is always a subset of T, because we're looking at elements of T, and all we're doing is removing those that also occur in the set S. And that's the last set minus operation. So now that we've defined these operations, let me summarize them. So first we saw how do you compare sets in terms of one being contained in the other. And if every element of a set S is contained or is also an element of the set T, I'm going to say that S is a subset of T. So this is the first operation. The second was the union operation. S union T is the set of all X that are either in S, or in T, meaning that you include any element in the union. You include any element that is at least an element of S or T, so at least one of them. And we looked at intersection, in which we're looking at elements that are in both sets S and T, not in at least one, but in both necessarily. And then finally, set minus, where all you do is take your set and remove any elements from the set you're doing the set minus of. So T set minus S is all the elements of T that are not in S. Right? So any element of T that is also in S, you remove it. And that's T set minus S. And these are the basic set operations that we're going to need for this class.